This is Anubhav Walia and I'll be telling you about memory systems. So let's start. Memory. What is memory? The main memory consists of a number of storage locations, each of which is identified by a unique address. You can see here address M1, address M2, address M3, address M4. The ability of the CPU to identify each location is known as its addressability. Each location stores a word, that is the number of bits that can be processed by the CPU in a single operation. Word length may be typically 16, 32 or as many as 64 bits. A large word length improves the system performance, though may be less efficient on occasions when the full word length is not used. Generally speaking, faster memory is more expensive than slower memory. To provide the best performance at the lowest cost, memory is organized in a hierarchical fashion. Small, fast storage elements are kept in the CPU. Larger, slower main memory is accessed through the data bus. Larger, permanent storage in the form of disk and tapes is still further from the CPU. So let's talk about memory hierarchy. This storage organization can be thought of as a pyramid. The base is magnetic tape, which takes 10 seconds to 3 milliseconds, and the upper part is optical disk, which takes 100 milliseconds to 5 seconds. And as we go up the structure, the cost increases. As you can see, magnetic tape is initially offline, optical disk is nearline, then followed by fixed rigid disk, which is online. Main memory is system, level 2 cache is also system, level 1 cache is also system, and registers is also system. As we go up the block, the access time decreases. As you can see, for registers it is only 1 nanosecond, and for level 1 cache it is 3 nanoseconds to 10 nanoseconds. Memory hierarchy. To access a particular piece of data, the CPU first sends a request to its nearest memory, usually cache. If the data is not in cache, then memory is queried. If the data is not in the main memory, then the request goes to the disk. Once the data is stored, then the data and a number of its nearby data elements are fetched into cache memory. Memory hierarchy. This leads us to some definitions. A hit is when data is found at a given memory level. A miss is when it is not found. The bit rate is the percentage of a time data is found at a given memory level. The miss rate is the percentage of time it is not, and usually miss rate is equals to 1 minus hit rate. It is an important formula and it needs to be remembered. The bit time is the time required to access data at a given memory level. The miss penalty is the time that it takes to replace a block of memory plus the time it takes to deliver the data to the processor. An entire block of data is copied after a hit because the principal of locality tells us that once a byte is accessed, it is likely that a nearby data element will be needed soon. There are three forms of locality. Temporal locality, recently accessed data elements tend to be accessed again. Spatial locality, access tends to cluster. Sequential locality, instructions tend to be accessed sequentially. So what are the types of main memory? There are two main types of main memory, which are random access memory, which is called as RAM, and ROM, read-only memory. Random access memory, or RAM, holds its data as long as the computer is switched on. All data in RAM is lost when the computer is switched off, described as being volatile. It is direct access as it can be both written to or read from in any order. Its purpose is to temporarily hold programs and data for processing. In modern computers, it also holds the operating system. Types of RAM. Dynamic random access memory (DRAM). Contents are constantly refreshed 1000 times per second. Access time is 60 to 70 nanoseconds, which is very less. Note, a nanosecond is 1 billionth of a second. Synchronous dynamic random access memory (SDRAM), quicker than DRAM. Access time less than 60 nanoseconds. Direct RAM bus dynamic random access memory (DRDRAM). New type of RAM architecture, access time 20 times faster than DRAM, more expensive. Static Random access memory RAM, SRAM, doesn't need refreshing, retains contents as long as power applied to the chip. Access time around 10 nanoseconds, used for cache memory, also for date and time settings as powered by a small battery. Now let's talk about cache memory. Small amount of memory, typically 256 or 512 kilobytes. Temporary store for often used instructions. Level 1 cache is built within the CPU. Level 2 cache may be on chip or nearby. Faster for CPU to access than main memory. Level 2 cache is external and level 1 cache is internal. The operation of cache memory. So let's talk about from the block diagram. The cache memory, SRAM, it can obtain information from main memory, which is DRAM, and it can also send or share information with CPU. The arrow mark basically shows the bus connection. As you can see, the cache memory has bus connection with CPU and main memory both. Cache fetches data from next to current address in main memory, and CPU checks to see whether the next instruction it requires is in cache. If it is, then the instruction is fetched from the cache a very fast position. If not, the CPU has to fetch next instruction from main memory, a much slower process. So in this way, we can tell about the cache. Now types of RAM. Video random access memory holds data to be displayed on computer screen, has two data paths along read and write to occur at the same time. A system amount of VRAM relates to the number of colors and resolution. A graphics card may have its own VRAM chip on board. Virtual memory uses backing storage, example hard disk, as a temporary location for programs and data when insufficient RAM available. Swaps programs and data between the hard disk and RAM as the CPU requires them for processing. A cheap method for running large or many programs on a computer system. Cost is speed. The CPU can access RAM in nanoseconds but hard disk in milliseconds. Virtual memory is much slower than RAM. Read-only memory. Now let's talk about read-only memory. ROM holds programs and data permanently even when computer is switched off. Data can be read by the computer in any order, so ROM is also a direct access. The contents of ROM are fixed at the time of manufacture. Stores a program called the bootstrap loader that helps start up the computer. Access time of between 10 to 50 nanoseconds. Types of ROM. Programmable read-only memory, PROM, empty of data when manufactured, may be permanently programmed by the user. Erasable programmable read-only memory, EPROM, can be programmed, erased and reprogrammed, which is different from PROM as it cannot be erased. So the EPROM, which has a small window on top allowing it to be erased by shifting ultraviolet light on it. After reprogramming, the window is covered to prevent new content being erased. Access time is around 45 to 90 nanoseconds. Electrically erasable programmable read-only memory, EEPROM. Reprogrammed electrically without using ultraviolet light. Must be removed from the computer and placed in a special machine to do this. Access time between 45 and 200 nanoseconds. Flash ROM, similar to EEPROM, however, it can reprogram while still in the computer. Easier to upgrade programs stored in flash ROM. Used to store programs in devices, example modems. Access time is around 45 to 90 nanoseconds. ROM cartridges, commonly used in games machines, prevent software from being easily copied. Now let's talk about semiconductor memories. The organization. The basic element of semiconductor memory is the memory cell. Semiconductor memory cells properties. They exhibit two stable or semi-stable states which can be used to represent binary 1 and 0. They are capable of being written into the state at least once. They are capable of being read to the state. The block diagram of memory cell operation. As you can see in right, select goes into cell, control goes into cell, and data input also goes into cell. Whereas in cell, select for the read mode, select goes into the cell, control goes into the cell, but the sense goes out of the cell. So in this way, information is shared. Semiconductor memory types. Memory types: category, erasure, write mechanism, volatility. We'll be discussing about them one by one. Random access memory. The category is read-write memory. Erasure is electrically byte level. Write mechanism is electrically. Volatility is volatile. ROM, read-only memory, and PROM, read-only memory for category, not possible for erasure, masks, and it is non-volatile. Erasable PROM, EPROM, electrically erasable PROM, EEPROM, and for flash memory, the category is read mostly memory. For erasure, it is UV light chip level, or electrically byte level, or electrically block level. Write mechanism is electrically, volatility is non-volatile. RAM. A dynamic RAM is made with cells that stores data as charge on capacitors. The presence or absence of charge in a capacitor is interpreted as binary 1 or 0. Capacitors have a natural tendency to discharge. Dynamic RAMs acquire periodic charge refreshing to maintain data storage. The term dynamic refers to this tendency of the stored change to leak away even with power continuously applied. DRAM cell. As you can see the diagram, it has a transistor which is connected to address line, and it is also connected to a storage capacitor. The storage capacitor is grounded with transistor, and the bit line is B. Typically, DRAM structure for an individual cell that stores one bit is address line is equals to read or write, transistor is equals to switch. Write, when in write mode, 1 is equals to high and 0 is equals to low. A signal is then applied to the address line, allowing a charge to be transferred to the capacitor. Read, address line. The transistor turns on and the charge stored on the capacitor is fed out onto a bit line. The sense amplifier compares the capacitor voltage to a reference value and determines if the cell contains a logic 1 or a logic 0. SRAM cell. As you can see, the DC voltage has 6 transistors, T3, T4, T1, T2, T5 and T6. T5 and T6 are connected to bit line, and T6 is connected to bit line B dash, complement of bit line B. T1 and T2 and T3 and T4 are connected to C1 and C2, and address line is connected to T5 and T6 also. SRAM cell, 4 transistors are cross-connected in an arrangement that produces a stable logic state. In logic state 1, C1 is high, C2 is low, T1 and T4 are off, T2 and T3 are on. In logic state 0, C1 is low, C2 is high, T1 and T4 are on, T2 and T3 are off. Both states are stable as long as the direct current voltage is applied. Unlike DRAM, no refresh is needed to retain data. SRAM versus DRAM, both volatile, power needed to preserve data. Dynamic cell, simpler to build, smaller, more dense, less expensive, needs refresh, larger memory units, and static is faster and has cache. Memory system performance metrics are miss rate or hit rate and average memory access time. Miss and hit rates are calculated as from the following formulas. Miss rate is defined as number of misses divided by number of total memory excesses, which is equals to 1 minus hit rate. Whereas hit rate is defined as number of hits upon number of total memory excesses equals to 1 minus miss rate. Miss rate plus hit rate is equals to 1. Calculating cache performances. Suppose a program has 2000 data access instructions and 1250 of these requested data value are found. The other 750 data values are supplied to the processor by main memory or disk memory. What are the miss rate and hit rates for the cache? I'll be pausing the video. You can pause the video now and work out this example. The miss rate is 750 upon 2000, which is equals to 0.375, roughly equals to 37.5%. The hit rate is 1250 upon 2000 is equals to 0.625, which is equals to 62.5%, which can be also calculated by subtracting from 37.5%. Average memory access times. AMAT is the average time a processor must wait for memory per load or store instructions. The processor first looks for the data in the cache. If the cache misses, the processor then looks in the main memory. If the main memory misses, the processor accesses virtual memory on the hard disk, and at the time increases time by time. AMAT is calculated as AMAT is equals to T cache plus MR cache TMM plus MRMM TVM. Calculating average memory access time. Suppose a computer has a memory organization with only two levels of hierarchy, a cache and a main memory. What is the average memory access time given? The access times and miss rates given in table. So the table is given with main memory level cache, access time 1, miss rate is equals to 10%. Main memory is equals to 100 and with a miss rate of 0%. The average memory access time is 1 plus 0.1 into 100, which is equals to 11 cycles. Let's talk about cache memory. A cache holds commonly used memory data. The number of data words that it can hold is called the capacity. C. When the processor attempts to access data, it first checks the cache for the data. If the cache hits, the data is available immediately. If the cache misses, the processor fetches the data from main memory and places it in the cache for future use. Now we see the block diagram of single cache. CPU is the leftmost part, the cache is the in middle, and main memory is on the right. The access between cache and CPU is very fast, whereas the between main memory and cache the access time is quite slow. So between the cache and main memory, block transfer happens, whereas for CPU and cache, word transfer happens. It is this block diagram was for single cache. Now let's talk about the three-level cache organization. CPU is connected with three types of caches, which are level 1 cache, level 2 cache, and level 3 cache. And level 1 cache is the fastest, level 2 cache is fast, and level 3 cache is less fast, and main memory is slow. And as you can see, CPU is connected with level 1 cache, and level 1 cache is connected with level 2 cache, level 2 cache is connected with level 3 cache, and level 3 cache is connected to main memory. If data is not found in these three caches, then the data is accessed in main memory, and the time taken for it is usually very high. Issues in cache design. Let's talk about the issues. To accommodate the new data, the cache must replace old data. What data is held in the cache? How is the data found? And what data is replaced to make room for new data when the cache is full? Let's talk about the structure of cache and main memory. As you can see, in a particular row, it has tag and block. And line numbers are 0, 1, 2, 1, 2 till C-1, and block lengths are k words for cache. Whereas in main memory address, 0, 1, 2, 3, 4 for block k words, and it goes on till 2n-1, and the width is word length. Now let's talk about the block diagram or the structure algorithm for this. Start. Receive address array from CPU. Now let's ask the question, is block containing array in cache? If the answer is yes, then we go on to fetch the word and deliver it to the CPU, and the process is finally done. If the block containing array in cache is not available, the answer is no, so it goes to access the main memory for block containing array, and it finally goes to allocate cache line for main memory. And then it can either go for load main memory block into cache line, or it can go to deliver array word to CPU, and finally the task will be completed. Typical cache organization. As you can see, the processor is connected to cache and address lines also, and is also connected to data buffer, and these all three are connected to system bus. As you can see, control is connected, has control over cache, and processor addresses it to the address buffer, and finally it goes to the system bus, and system bus also has control over cache, and processor also has the data flowed with data buffer, and it finally goes to system bus. Elements of cache design: cache addresses, logical, physical, cache size, mapping functions, direct associative, set associative, replacement algorithm, least recently used, LRU, first in, first out, FIFO, least frequently used, LFU, random, write policy, write through, write back, write once, line sizes, number of caches, single or two level, unified or split. Cache addresses. Virtual memory is facility that allows program to address memory from a logical point of view without regard to the amount of main memory physical available. When virtual addresses are used, the system designer may choose to replace the cache between the processor and MMU or between the MMU and main memory. A logical cache, also known as virtual cache, stores data using virtual addresses. The processor accesses the cache directly without going through the MMU. And as you can see, we have already discussed the block diagram of the logical cache. For physical cache, we have a physical cache stores data using main memory physical addresses. The processor is connected to MMU, which is connected with physical addresses of cache, and the data flows between the processor and main memory in this fashion. Cache size. Size of the cache to be small should be small enough so the overall average cost per bit is close to that of main memory alone. Large enough so that the overall average access time is close to that of the cache alone. Mapping function. The transformation of data from main memory to cache memory is referred to as mapping. Three types of mapping procedure, which are associative mapping, direct mapping, set associative mapping. Now let's take an example. Main memory can store 32K words of 12-bit each. Cache is capable of storing 512 of these words at any given time. For every word stored in cache, there is a duplicate copy in main memory. Main memory 32K into 12, which is connected to CPU. CPU is connected to cache 512 into 12. Associative mapping. CPU address 15, argument register address data. Address is 0100, then data is 3450. Address is 02777, data is 6710. Address is 22345, then data is 1234. Fastest and most flexible cache organization uses an associative memory. The associative memory stores both address and content of the memory word. This permits any location cache to store any word from main memory. Address 15 and data 12. A CPU address of 15 bits placed in the argument register and associative memory is searched for matching address. If address is found, the corresponding 12 bits is read and sent to the CPU. If no match occurs, the main memory is accessed for the word. The address data is then transferred to the associative cache memory. If the cache is full, an address data pair must be displaced to make room for pair that is needed and not presently in the cache. Replacement algorithm is a simple round-robin FIFO, which is first input, first output. Now let's talk about direct mapping. Associative memories are expensive compared to random access memories because of the added logic associated within each cell. The number of bits in each index field is equal to the number of add bits required to access the cache memory. Here we take the block diagram, which has 6 bits as tag, 9 bits as index. The tags send the data to octal addresses, which is 00 till 77, and index sends the data to 000, which is till 777, and main memory has a size of 32K into 12. Addresses are 15 bits and data are 12 bits, and cache memory has a size of 512 into 12, and address is 9 bits and data is 12 bits. The index also sends the data to cache memory with octal addresses 000 and 77 up till 777. 2K words in cache memory, 2 in mm. N bit divided into fields k bits index and nk for tag field. As you can see in the main memory address is 0000, then the data stored is 1220. For memory address 00777, the data stored is 2340. For memory address of 0200, the main memory is 5670. For 0277, it is 6710. For index address, the tag is 00, data is 1220 for 000, and it goes up down till 777. The tag becomes 02 and the data becomes 6710 in cache memory. In a 512 cache, there are 64 blocks of 8 words each. Since 64 into 8 is equals to 512, block number is specified with a 6-bit field and the word within block is specified with a 3-bit field. Tag field stored within the cache is common to all words of the same block. Entire block is removed every time a miss occurs. Now let's talk about direct mapping. The simplest technique, known as direct mapping, maps each block of main memory into only one possible cache line. The mapping is expressed as I is equals to j modulo n, where I is equals to cache line number, j is equals to main memory block number, m is equals to number of lines in the cache. As you can see, the previous example we discussed of mapping was a block size of 1 word. Now direct mapping with block size of 8 words. Here block 0 has index, tag and data, and so on. And if in a 512 word cache there are 64 blocks of 8 words each, since 64 into 8 is equals to 512. Block number is specified with a 6-bit field and the word within the block is specified with a 3-bit field. Tag field stored within the cache is common to all 8 words of the same block, and tag block is removed every time a miss occurs. Set associative mapping, the only disadvantage of direct mapping. 2 words with same index in their address but with different tag values cannot reside in cache memory at the same time. Set associative mapping, each word of cache can store 2 or more words of memory under the same index address, and each data word is stored together with its tag, and the number of tag data items in one word of each cache is set to form a set. Address length is equals to s plus w bits, and number of addressable units is equals to 2 power s plus w words or bytes. Block size is equals, or line size is equals to 2 power w words or bytes, and the number of blocks in main memory is equals to 2 power s, where size of tag is s bits and the number of line in cache is undetermined. So in each index refers to 2 data words, tag 6 bits, data words 12 bits. Word length is equals to 2 into 6 plus 12, which is equals to 36 bits. Index address of 9 bits is equals to 512 words, and cache memory is equals to 512 into 36, which is equals to 1024 words of main memory. Now let's talk about replacement algorithm. When a miss occurs in a set associative cache and set is full, it is necessary to replace one of tag data items within a new value. Most common replacement algorithm used is FIFO, and least recently used. With random replacement policy, control choose one tag data item for replacement at random. FIFO procedure selects for replacement the item that has been in the set of the longest, and LRU algorithm selects for replacement the item that has been least recently used by CPU. Writing into cache. When a CPU finds a word in cache during read operation, the main memory is not involved in transfer. If operation is right, there are 2 ways that system can proceed: write through. Simple and most commonly used procedure is to update main memory with every memory write operation, with cache memory being updated in parallel if it contains the word at the specified address. Advantage is main memory always contains the same data as the cache. This characteristic is important with direct memory access transfer. Now let's talk about write back method. Only the cache location is updated during write operation. The location is then marked by a flag so that later when the word is removed from cache, it is copied into main memory. The reason for the write back method is that during this time a word resides in cache, it may update several times. However, as long as the word remains in the cache, it does not matter whether the copy in main memory is out of date, since the requests from words are filled from cache. It is only when the word is replaced from cache that an accurate copy needs to be rewritten into main memory. Now let's take a problem and let's discuss it in detail. A digital computer has a memory unit of 64K into 16 and a cache memory of 1K words. The cache uses direct mapping with a block size of 4 words. Now let's calculate how many bits are there in tag, index, block and word fields of the address format. How many bits are there in each word of the cache and how are they divided into functions? Include a valid bit. How many blocks can the cache accommodate? Now let's take the solution. Since the memory capacity was 64K into 16 and cache capacity was 1K into 16, so for block direct mapping with block size of 4 word, the memory space will be equals to 2 power 6 into 2 power 10, which gives equals to 2 power 16. Therefore 2 power 16 words is in memory. Therefore 16 bits are required to address the 2 power 10 memory. Cache words, 10 bits are registered to address the cache. Tags is equals to 6 bits and index is equals to 10 bits. Cache divided into blocks of 4 words. Number of blocks is equals to 256 blocks, as 2 power 10 by 2 square is equals to 2 power 8. Tag bits plus data word bits plus valid bits is equals to 6 plus 16 plus 1, which gives rise to 23 bits. And blocks is equals to 2 power 8, which is equals to 256 blocks. Now let's take another problem. Let's calculate how many 128 into 8 RAM chips are needed to provide a memory capacity of 2048 bytes, and how many lines of the address bus must be used to access 2048 bytes of memory. How many of these lines will be common to all chips? How many lines must be decoded for chip select? Specify the size of decoders. It is an important question, and these types of questions were recently asked in our CAT exams. Now let's take the solution of this problem. Solution: 2048 by 128 gives rise to 16 chips. So 16 chips will be required. As the first question which basically asked was how many lines, how many chips are needed to provide a memory capacity of 2048 bytes. So the answer is 16 chips. And 2048 is equals to 2 power 11 and 128 is equals to 2 power 7. So for 2048, 11 lines are needed, and for 128, 7 lines are needed to address each chip. 4 lines to decoder for selecting 16 chips. 4 into 16 decoder. Virtual memory. Give the programmer the illusion that system has a very larger memory, even though the computer actually has a relatively small main memory. This is the basic concept behind the virtual memory. The address space and memory space. Translation or mapping is handled automatically by hardware by means of mapping table. As you can see the block diagram of this virtual address, and this needs to be remembered. Virtual memory. Large memory space were available equal to the totality of auxiliary memory. VM system provides mechanism for translating program generated address into correct main memory location. This is done dynamically while PGM are being executed in CPU. Now let's talk about address space and memory space. Address space, an address used by a programmer, is called virtual address, and the set of such address is called address space. Address space is the set of address generated by programs as they reference instant and data. Memory space, an address in main memory, is called a location or physical address. Set of such location is called memory space. Memory space consists of actual main memory location directly addressable for processing. Address space is allowed to be larger than memory space in computer with virtual memory. Now let's take an example. Consider a computer with main memory capacity of 32K. K equals to 1024. 15 bits are needed to specify a physical address in main memory, since 32K is equals to 2 power 15. Suppose that a computer has available auxiliary memory for storing 2 power 20 is equals to 1024k words. Thus auxiliary memory has capacity for storing information equivalent to capacity of 32 main memories. Denoting address space by n and memory space by m, for this example, n is equals to 1024k and m is equals to 32k. Program and data are transferred to and from auxiliary memory and main memory based on demand imposed by CPU. Suppose program 1 is currently being executed in CPU. Program 1 and portion of its associated data are moved from auxiliary memory to main memory. Portions of the program and data need to be in contiguous location in memory. Since the information is being moved in and out, and empty spaces may be available in scattered location in memory. Address field of the instant code has sufficient number of bits to specify all virtual memory. Address field of the instant code will consist of 20 bits, but physical memory address must specify with only 15 bits. Thus, CPU will reference instant and data with 20 bits address, but information at this address must be taken from physical memory because access to auxiliary storage for individual words will be long. A table is then needed to map a virtual address of 20 bits to a physical address of 15 bits. Mapping is dynamic operation, which means that every address is translated immediately as word is referenced by CPU. The memory table for mapping a virtual address. The virtual address is connected to memory mapping table, which is connected to memory table buffer register, which is connected to main memory address register, and which is connected to main memory, and main memory is finally connected to main memory buffer register. Mapping table may be stored in separate memory or in main memory. Case 1, additional memory unit is required as well as one extra memory access time. Case 2, table space from form mm and 2 access to memory are required with PGM running at half speed. Case 3, use associative memory. Virtual memory, address mapping using pages. Physical memory is broken down into group of equal size called blocks within which may range from 64 to 4096 words each. Page refer to group of address space of same size. Example, if a page or block consists of 1k words, then using previous example address, space is divided into 1024 pages and main memory divided into 32 blocks. Page is equals to address space block memory space. Now here we have the example with address mapping. As you can see, the address space is equals to n is equals to 8k is equals to 2 to the power 13. So we have 7 pages, and memory space is equals to m equals to 4k 212. So organization of memory mapping table in paged system. We have the page number as 101, or it can change to 000, 001, 010, 011, 100, 101, 110, 111. And basically it is this block diagram can be referred to the previous theoretical taught. Mapping from address space to memory space is facilitated if each virtual address is considered to be represented by two number page number no and a line within page. In a computer with 2p words per page, p bits are used to specify a line address and remaining higher order bits of virtual address specify a page number. Virtual address has 13 bits since each page consists of 2 power 10 is equals to 1024 words. Higher order of 3 bits of virtual address will be specify one of 8 page and low order 10 bit given line address within the page. Line address in line address space and memory space is the same, only mapping is required from page number to block number. Now this was the origination of memory mapping. A read signal to mm transfer the content of the word to the mm buffer registration ready to be used by CPU. If the presence bit in the word read form the page table is 0, it signifies that the content of the word referenced by VA does not reside in mm. A call to the OS is then generated to fetch the required page from auxiliary memory and place it into mm before resuming computation. We have the associative memory page table. And now let's talk about page fault. When a program starts execution, one or more pages is transferred into main memory and the page table is set to indicate their position. The program is executed from main memory until it attempts to reference a page that is still in auxiliary memory. Page number cannot be found in the page table is called page fault. So this is called as page fault. Present program is suspended until the required page is brought into main memory. Replacement algorithm is for FIFO or I'll argue. This is the M hardware. In multi-programming environment, moving data and program in and around the memory is important without changing the other programs. Memory management system is a collective of hardware and software procedures for managing the various programs residing in memory. The basic components are this dot. Okay, this is logical to physical address mapping. This is a TLB, and we have concluded this using the TLB and the logical to physical address mapping. So we conclude the memory topic. Now I thank you for giving, I thank personally Professor Dhanapal for giving me this opportunity to make a video on memory units. Thank you.